Okay, so previously we have dealt with discrete random variables. So just to recall, okay, so for example, if let's say I throw a fair die, how many outcomes do I have? 6 outcomes. Okay. Is it possible that I only have 2 outcomes when I throw a fair die? Would that be possible? Okay, the answer is yes. Okay. You find that no matter what experiment you are doing, I can always restrict it to 2 outcomes. Okay, so why is that so? For example, when throwing a fair die, I have outcome 1 to outcome 6. But I can also say that the outcome is 6 or not 6. If let's say I'm interested in whether or not the die will land at 6. Okay? So I can always restrict any experiment to only 2 outcomes. And that is what we are going to do today. We are going to look at experiments and we are restricting them to 2 outcomes only. And you'll find that there's actually many things that we can do if an experiment only has 2 outcomes. Okay, so I'll write down here. Last time we dealt with DRV. Okay, and we know that DRV can have many outcomes. Okay, but we are only going to look at experiments that only has exactly 2 outcomes. And we give it a special name, okay, because as you know, bicycle, it means that it has 2 wheels. And if an event is held biannually, it means that it's held every 2 years. So therefore, for a random variable with 2 outcomes, we call it a binomial random variable. Okay, so the bi will stand for 2 outcomes. With that, let us take a look at the first example, example 5. Okay. Example 5, I let x be the number of sixes obtained when 3 dice are thrown. Find the probability distribution function of x. Okay. Can you help me to change the question down here? Okay. When 3 dice are thrown, I would like to change the context a little bit. Okay. You change it to when a fair die is thrown 3 times. So if we look at this statement here, I'm actually interested in the number of sixes that I obtain. Okay. So in other words, I can restrict the outcome to 2. If it is a 6, then it's good. Okay, it belongs to a so-called a success condition that I stated because I'm interested in the number of sixes. Okay, and then the other outcome will be not 6. Or I can also call it 6 prime. Okay, so I can restrict it to 2 outcomes. This is the first time that we are seeing this term, probability distribution function. Okay. In DRV, you have seen it, but you have not seen it in action. So today, we are going to see how to find the probability distribution function. In DRV, we dealt with this, probability distribution. Do you still remember what is this? You still recall? What is a probability distribution? And how do I represent it? Okay. So just to recap your memory a little bit, probability distribution is actually presented in the form of a table form. So for example, okay, if I scroll back, okay, something like this. This table that you see is actually a probability distribution. Okay, so meaning we list out all the possible values of x
and all the probabilities corresponding to all the possible values. So this is a probability distribution. Okay. So today we are going to deal with probability distribution function. So it's no longer a table. I just make a note here. Okay, draw a table. But if I'm dealing with probability distribution function, PDF, it's essentially a function that I need to come up with, or in other words, a formula. Okay, I need to come up with a formula that will summarize all the probabilities for the possible values that it can take. Okay, so in other words, I will need to do some pattern recognition. I need to spot some pattern in order to identify the formula. But in order to spot the pattern, first of all, I have to list out all the individual probabilities first in order to identify a formula that can help me to summarize everything. Okay, so let's do that. We try to solve this question first. So in one toss, we either get a 6 or not a 6. And probability of getting a 6 is 1 out of 6. Okay, this one we all know. Probability of getting not 6 will be 5 out of 6. In 3 tosses, altogether there will be 8 outcomes. So why is there 8 outcomes? I throw 3 dice. Okay, the first die, I can have 2 outcomes. Either a 6 or not a 6. Same thing for the second die and also the third die. So altogether, I will have 8 outcomes. And the values that X can take will be 0, 1, 2, or 3. Okay, because when I throw a die 3 times, I can either have no 6s, or if I'm lucky enough, I will have all the throws give me 6s. So it can be 0 all the way to 3. Okay, these are the possible values that X can take. So when X is equals to 0, it will mean that I have no 6 at all. Okay, no 6. That means it's all 6 prime, 6 prime, and 6 prime. Okay. So we can easily fill up the tree diagram. It will just be 1 out of 6 and 5 out of 6 all the way. Okay, so I'll leave you to fill in the details yourself. Now let's try to find the probability that X is equals to 0. Okay, so if I were to have 6 prime, 6 prime, and 6 prime, okay, so which means the first die that I throw, the chance of getting not a 6 will be 5 out of 6. Similarly, for the second die, the second throw, it will be 5 out of 6 as well, and 5 out of 6. So I can summarize this using 5 over 6 cubed. This is a chance that all the 3 throws will actually give me not 6. Next, probability that X equals to 1 means that I will have 1 6 only, exactly 1 6. So I will have this 6, and then not a 6, not a 6. Okay. So let's try to find first. For now, we ignore the times 3. So the chance that my first throw will be a 6 is 1 out of 6. Second throw is not 6. Third throw is not 6. So I have 5 out of 6 squared. Okay, then after that I ask myself, why do I need to multiply by 3? Just now we found this probability. Okay, 6, not 6, not 6. But I can also have the throw to be as such. The first throw is not a 6. Second throw is a 6. Third throw is not a 6. This is also a possibility down here. Okay, so if I were to find this probability, 5 out of 6 times 1 out of 6 times 5 out of 6. you find that it's exactly the same. You give me the same value as just now. Okay. Just now was 1 out of 6 times 5, 6 times 5, 6. Notice that they'll give me the same value. And similarly, I also have a third case, not 6, not 6, 6. So altogether, I can have 3 cases in total. Okay, so we realize that actually they give us the same probability. Altogether got 3 cases. You realize that down here I can actually do a listing down because it's only 3 cases. But is there a more systematic way for me instead of just listing down? Okay, so if I were to take a look here, do you realize that actually it's just a permutation of this? It's just an arrangement of 6, not 6, and not 6. I'm just trying to find out how many ways can I arrange this. Okay, so it's actually a P&C question. Out of the 3 spaces, I need 1 space to be a 6. So therefore, I can do a 3 choose 1. Okay, so that's how I obtain the 3. Okay, so back to here. I'll write a 3 choose 1 over here. Okay, now I do the same thing for x is equals to 2. If x equals to 2, it means that I need to have exactly 2 6s, and one of them must be not a 6. So if I find it in this particular order, first row is a 6, second row is also a 6, so I can put a square here. Third row is not a 6, therefore it will be 5 out of 6. Again, I need to find the total number of cases down here. So this time round, because there are 2 6s, I can think of it as out of the 3 space, I need to choose 2 spaces for the 6. So therefore it is 3 choose 2. In fact, it is also 3 cases. Okay, so if I were to list it down, it would just be these 3 cases. I just make a note here. Okay, 3 choose 1 is actually the number of ways to arrange 6, 6 prime, and 6 prime. Okay, so that's how I obtain the 3 choose 1. Okay, last but not least, if I were to have x equals to 3, it means that all of the throws will give me 6. Okay, so first throw give me 6, second throw give me 6, third throw give me a 6. So therefore it will just be 1 out of 6, the whole thing cubed. Okay, again remember our purpose. We are doing all this because we want to find a formula that can actually summarize all this for us. Okay, so that when I just substitute a value, let's say x equals to 1, I just substitute 1 inside the formula, I'll be able to find the associated probability. So that's our purpose. Okay? So we try to spot a pattern here. If you notice, for x equals to 1 and x equals to 2, I have 3 terms. But for 0 and 3, I only have 1 term. So let's try to increase x equals to 0 and x equals to 3 to 3 terms. We try to make it into the same format. Okay. So how do we do that? Let's try. We try to spot the pattern here. I see a 3 choose 1 and a 3 choose 2 here. So I will put a 3 choose 0 down here. Am I changing the question in any way when I put 3 choose 0? Am I changing the value? No, right? 3 choose 0, the value is 1. So I'm not changing the value in any way. Can I also do this? I put a 1 out of 6 to the power 0. Am I changing the value? Also no, right? I'm still multiplying by 1. Okay. This is because when I look at the power of 1 over 6, I notice that down here the power is 1. Okay, I can actually put a 1 here, and then the power here is 2. So logically, I would think that the power on top should be power 0. And then I put back my 5 over 6 cube. So notice that I'm not changing the value in any way. I'm introducing a 1 down here and introducing a 1. Okay, I can do the same thing for x equals to 3. I put a 3 choose 3. Again, not changing value because 3 choose 3 is 1. 1 over 6 cube will remain. And I will put a 5 over 6 to the power of 0. Okay? This is because when I try to spot the pattern, I notice that the power of 5 over 6 keep on decreasing. Down here was 3, 2. Down here is 1. And logically, I should think that the power here will be 0. Okay? So right now, can we spot the pattern? Are we able to see the formula now? Okay, right? Okay, you should be able to see a formula. The first thing we should realize is that on top of the choose operation is always a 3. The bottom, okay, 3 choose something, it will correspond to your x value. So when x is 1, it will be 3 choose 1, so on and so forth. So when I try to write a formula, when x is equals to r, it will be 3 choose r. And notice the power of 1 over 6 is actually the same as your x value as well. Okay, so in this case, when x is r, 1 over 6 will be raised to the power r. Okay. So I'll make a note here. Okay, they will be the same. The last thing that we need to realize is the power of 5 over 6. Notice that the power of 5 over 6, when added to the power 1 over 6, it will give me 3. So same here, 2 plus 1 will be 3, 1 plus 2 will be 3. Okay, so therefore, when I do a sum of the powers, it must give me sum to 3. So therefore, the power here will be 3 minus r. Okay, so that's how we come up with the formula, which is known as the probability distribution function, in short, PDF. Okay, so if you notice for this experiment, the experiment consists of 3 repeated trials because I throw a fair die 3 times. Okay, 3 repeated trials. Each trial has 2 outcomes. Either a 6 or not a 6. Each trial is independent. Okay, so that means my first throw, if let's say I throw a 3, does it affect my next throw? No, right? It doesn't affect. Okay, it doesn't affect the outcome of the next throw. So this means that each trial, or in this case, each throw of the die is actually independent. Okay, because it's not affected by other throws. And of course, we realize that the probability of getting a 6 in any one throw is actually the same. It is equals to 1 out of 6. So these are the 4 things that we should observe from the previous experiment. Now can you spend some time to read through example 6 first? Oh, okay. I missed one statement. Down here, probability that x equals to r is given by this formula, and we know that the random variable x is is known as a binomial random variable. Okay, what have we learned about random variables? There is one thing that we learned. If I were to sum up all the probabilities, what will happen? It will be equals to 1. Okay, so if I sum from r equals to 0 to 3, it will give me the value 1. Okay, now can you spend 3 minutes to read through the next example and help me fill in the tree diagram? Is it better with the lights? Better, but can you all see on the screen? Okay, who prefer the lights off? Oh, okay, who prefer the lights on? Okay, I think it's only me. Read the tree diagram first. Okay, so first of all, we have to realize that for this question, it is without replacement. So help me to highlight this. Okay. This is a very important phrasing. Okay, because you'll find that the situation is different with or without replacement. Okay, so actually for this kind of question, it's pretty fast to fill up the tree diagram. We have to realize that after you take a ball, or a counter in this case, then you have one lesser counter to choose from. So the overall counter will actually decrease by 1. Okay, so which is why all the second branches you'll be over 8. And then for the final one, the final branch, it'll be everything over 7. Okay. If I have 3 black balls and I select one black ball, I'll be left with 2, and then I'll be left with 1 to choose from. Okay, same thing for the white ball. If I start off with 6, I choose one white ball, I will have 5 and then 4. And individually, I know that within each branch that branch out from the same point, they must give me a sum of 1. So therefore, I can fill in the numbers from here. Okay, and lastly, if I have 6 white balls left, and I select one white ball, I'll be left with 5. And then here will be 2. Okay, and the final one will be 2 and 5. Okay, so this is our tree diagram. Okay, so let y be the number of black counters drawn. When y is equals to 0, it means that I have no black counter. So in other words, the 3 counters that I draw will all be white counters. Okay. So using the tree diagram, okay, I can easily find out what is the probability. It's actually the last branch over here, when all the counters are white. Y equals to 1 means that I will have one black counter. So I can write it as such. Assuming the first counter is black, I can first find out what is the probability of black, white, white. Okay, but I still need to multiply by 3 later on. So following the branch, okay, black, white, white. Okay, you can easily show that if I were to find the probability of white, white, black, for example, it will still be the same value. Okay, so which is why I can just multiply by 3. Okay. So let's try. If let's say I want to find white, white, black, what is the probability? Okay, so we try to write down 6 over 9 times 5 over 8 times 3 out of 7. Okay, this is for white, white, black. So if we compare now, do they look like they are the same value? So we compare this with this. Do they look the same to us? Okay, at first glance, maybe not. Because down here I see that there is a 6 out of 9, but down here I don't have a 6 out of 9. So on first glance they may look a bit different, okay, but if I just put your focus to the numerator first. Numerator is 3 times 6 times 5. If I look at the numerator here, I also have 3 times 6 times 5, just that it's in a different order. Okay, denominator, 9 times 8 times 7, and here is the same, 9 times 8 times 7. Okay, so essentially, if I were to find out all 3, they will still give me the same value. So actually, it's not necessary to do that. I will just need to multiply by 3. Okay, this is just for your own reference only. Okay, then after that, we can find out probability y equals to 2. So I can take probability of black, white, white, and again, I need to multiply by 3. Black, black, white. Okay, so it's 3 out of 9. Okay, times 2 out of 8. Times 6 out of 7. And remember to multiply by 3. Okay. And actually the last one without any calculation, are you able to tell me what's the value? Notice that this is also a random variable. So therefore, if I were to sum up all the probabilities, it must give me 1. Okay? But just to do a check, So for probability that I have 3 black counters, essentially I'm looking at the first branch. So this will be equals to 1 over 84. Okay, during your exam, if let's say this is the exam question, okay, after you do all this, do you stop here? Yes. Okay, very good. Okay, for me I wouldn't. What do you think I would do? How do I do a quick check, a very quick check that all my values are correct? I just add them together and they must give me the value 1. Okay, so during your exam, always perform a check. So if I were to sum all this, it must sum up to 1. Now, if we compare the 2 examples just now, okay, notice that both experiments, they consist of 3 repeated trials. Just as for the first one, I throw a die 3 times. Then now, I draw a counter 3 times. Okay. Each trial has 2 outcomes, as we can see. Also in example 5, each trial is independent. Probability of getting a 6 in any throw is the same. But what about for the current experiment that we are doing? You notice that condition 3 is not satisfied, meaning the trials are not independent. Okay, so can we show that using numbers? Because if we just explain like this, probably it's not so clear. If I want to show that events A and B are independent, how do I show? Okay, so we should be very familiar with this. There are 3 formulas that we can show. We just need to show one formula is true, then we can show that A and B, they are independent. Okay, for a short form, I'll just write IND to represent independent. Okay, so recall the formula. Probability that A given B must be equals to probability of what? A. Okay, so this is one of them. And then of course we also have the opposite. Okay, that one is obvious. We also have probability of A intersect B equals to PA times PB. Okay, please take note that this formula cannot be applied anywhere. Okay, so for your exit pass, okay, this is actually an error. So some of you went to multiply them together. Okay, so if question asks for A intersect B, we cannot apply this formula straight away unless the question states that events A and B are independent. Okay, if not, if question never states, then we need to find other ways to find out the value. Okay, so for the purpose of this, I'll actually show using the first one, the first formula. Let me define 2 events first. Okay, I'll define 2 events, B1 and B2. B1 will be the event that the first counter is black, and B2 will be the event that the second counter is black. Let's try to find what is probability of B2 given B1. The chance that my second counter is black given that my first counter is black. So are we able to see this value straight away? from the tree diagram, can we see this value? What is the probability that the second counter is black given that the first counter is black? It will just be 2 over 8. That is the value. Okay, now let's try to find what is probability of B2. That the second counter is actually a black counter. So referring back to our tree diagram, actually I have 2 branches. The first branch, okay, this one will give me a second black counter, and I can also have this branch, selecting a white first and then a black. It will also result in the second counter being black. So altogether I got 2 branches. Okay. So I'll add up these 2 branches. And I find that it will give me a value of 1/3. So therefore I can make a conclusion. Probability of B2 given B1 is not equals to probability of B2. Okay, and therefore, I can conclude that B1 and B2, they are not independent. Okay, so we have just proven that in this experiment, selecting a black ball is actually not independent. That means the first ball, if I select a black one, it will actually affect the chance of my second ball being black. Okay? So it will affect. So in this case, we say that this is not a binomial random variable. Okay, so notice just now the first experiment, the trials are actually independent. So maybe this throw, I throw a tree. It doesn't affect my next throw. But if I were to look at this experiment here, the one selecting the black counter, okay, notice that it will actually affect. So let's summarize. We have looked at 4 properties so far. Okay, some of you are still copying. If you are done, you can look at the next page, which actually state the properties of a binomial experiment. Okay, so there are 4 properties in total. There is actually a mnemonic to help us to remember these 4 properties. First property, the experiment must consist of a fixed number of trials. Okay, meaning it must be finite. It cannot go on forever. There must be a fixed number. Okay. The trials are independent of each other. That means when I perform the experiment this time, it doesn't affect the outcome of the next experiment. Thirdly, each trial has 2 possible outcomes, either a success or a failure. And lastly, the probability of success is the same in each trial. So these are the 4 properties. As long as one condition is not satisfied, it is not a binomial experiment. Okay, all 4 conditions must be satisfied. So I make a note here. All conditions must be satisfied. So actually, to show that it is not a binomial experiment is very simple. I just need to state one condition that is violated, and it will no longer be a binomial experiment. Okay, as long as one is violated, that's it. So the mnemonic is as such. Fixed number of trials, we use a F. Independent is a I. Two outcomes, T. Probability same S. So you can remember it as FITS. That is the mnemonic. A very common type of question that will come up is as follows. Okay, how should we pronounce it? Mnemonic. Mnemonic. Okay, never mind. Okay, so two assumptions. Normally, question will ask for either one assumption or two assumptions. Okay, so we look at the four. Which one do you think is obvious? The obvious one we don't need to state. We look at the four conditions. Okay, usually, A and C, they are the obvious one. Okay, the obvious conditions. From the question, you can immediately see there are two outcomes. You can immediately see the number of trials. Okay, so when the question asks for assumptions, do not state these two. We will state the independent condition. Okay, that the trials are independent, and the fact that the probability of success is constant. But in the question, if you say like this, probability of success is constant, you will not get the mark. Okay, because you need to state it in the context of the question. We'll look at some examples later on and also inside your tutorial, okay, of how to state the condition in the context of the question. Okay, then therefore help me to highlight this. Statement B and statement D. These two are very important. Okay, and I repeat again, this is a very common type of question. Usually it's 1 mark or 2 marks. Okay, now here's the important thing. So far we haven't dealt with how to define a binomial random variable. Okay, so the way to define is as follows. We let x be the number of successes in n trials of a binomial experiment. So this is the way that we define. You need to write down this statement again in context. So I cannot just write down this. It must be in the context of the question. Where probability of success, I let it be small letter p. Probability of failure will therefore be 1 minus p. I use another symbol. Okay, in this case, I use a letter q. After we write down this statement, you need to write down the binomial notation, which is this. X follows a binomial distribution. Number of trials is n. Probability of success is p. Okay. So the notation is as follows. This symbol here, it represents follows. X follows a binomial, okay, B for binomial. N is your number of trials. So that means if I throw a die 10 times, I will write down 10 over here. P is the probability of success. So for example, if let's say I have this, I let x be the number of 2 obtained when I throw a fair die, okay, ten times. So can you try to write down the notation for this? Okay, given that this is the definition of the binomial random variable. So it should be pretty simple, right? Okay, to write down the notation. Take note, when defining the binomial random variable, I always need to write down the number of trials. Okay, just give me one more moment. So if you recall, the first entry is actually number of trials, which is 10. Second entry is probability of success. In this case, my success is actually the condition stated here, obtaining a 2. Obtaining a 2 will be my success. So therefore, it will be 1 out of 6. Okay. So we'll stop here for today. Tomorrow we'll carry on with binomial. Okay, can the class reps return to me the class list?